Learning Outcome 5.2. Perform calculations with the discrete time Fourier transform. In Chapter 4, you worked with the continuous time Fourier transform, and several of the learning outcomes were to do calculations with it. I want to focus on these 5 learning outcomes and make sure that you can transfer your knowledge from Chapter 4 into Chapter 5 working with the discrete time Fourier transform. Here in Chapter 5, we're combining all of these calculations into one learning outcome. In Chapter 4, learning outcome 4.5 was to calculate the frequency response and impulse response given linear constant coefficient differential equations. Well, we're going to take this learning outcome, and in Chapter 5, it's almost the same, but instead of differential equations, we have difference equations. You've seen them before. Your book introduces them with this notation. You see this in lab also, the common notation used for difference equations, sometimes called ARMA models, autoregressive moving average. Discuss that in lab. Just to make sure you're working with this okay, expand those summations. For each of these k values, goes from 0, 1, 2, up until n, here where it ends 2, but it goes until some arbitrary n. On the right side, again the k starts at 0, 1, and then 2, until some arbitrary m. So for instance, if we have this, it's in this form. Our n value is 1, because the largest value on the left side is 1. Our m value is 0, largest value on the right side is 0. Our a0 is 1, it's the unwritten coefficient for y of n. Our a1 is 2. Our b0 is 1, another unwritten coefficient. Now we want to use these difference equations and find the frequency response and impulse response. Well, what was the frequency response? Oh yeah, h of j omega. But here it's going to be h of e to the j omega. But we do the same thing. In Chapter 4, you had a differential equation, and we took the transform of each term. Well, here we're also going to take the transform of each term, but it's the discrete time Fourier transform, group like terms, and we know that y of e to the j omega will be x of e to the j omega times h of e to the j omega. Therefore, h of e to the j omega is this. How do we get the impulse response? We take the inverse discrete time Fourier transform of this. Just look in Table 5.2 for that. And you'll see us taking some inverse transforms in the next section. Next, recall back in Chapter 6, you learned how to calculate the response of applying a given input signal to a system described by a linear constant coefficient differential equation. For Chapter 5, same thing, but differential equation again becomes a difference equation. So there's our difference equation. There's the frequency response to it. If that's our input, by Table 5.2, you will find this as a transform of that particular time signal. Our output will be the transform of our input times our frequency response. So we have the transform of our input times our frequency response. Partial fractions, it's the same thing, but a little tiny hint. Now you're looking at what value of e to the minus j omega makes this whole term go to 0. That's going to be positive 1/3. Cover that up, plug in positive 1/3 here. 1 divided by 1 plus 2 times 1/3. 1 plus 2/3 is 5/3. 1 divided by 5/3 is 3/5. Likewise, what value of e to the j omega makes this whole denominator go to 0? E to the negative j omega equals negative 1/2. Plug in a negative 1/2 here. 1 minus 3 times minus 1/2 is 1 plus 3/2. That's 5/2. 1 divided by 5/2 is 2/5. Same thing, just watch that you're trying to find the value of e to the negative j omega that makes your denominator go to 0 and not just the value of omega. Then again, table 5.2, property number 8 will allow you to invert the transform of both of these. Remember the u of n, your answer is not correct without it. Okay, finally, chapter 4, you had learning outcome 4.7, which was 3 parts. Given 2 things, calculate a third using the Fourier transform. Well, we've got the same thing here, but instead of x of t, h of t, y of t, we have x of n, h of n, y of n. And instead of y of j omega, we have y e to the j omega. Instead of using just the regular Fourier transform, the continuous time Fourier transform, you're going to use the discrete time Fourier transform. So we have y of n is equal to x of n convolve h of n, just like in chapter 2. Fourier transform of this, y of e to the j omega, is x of e to the j omega times h of e to the j omega, convolution property, table 5.1. Take the 2 things we know, calculate our transform, from them calculate the third, and return our value back to calculate y. If you're given the 2 other items, likewise, take the transform of them, calculate the thing you don't know, and then take the inverse transform. If you're given 2 other items, calculate the transform of them, calculate the transform of the thing you're looking for, and calculate your inverse transform. Same thing as in chapter 4. I'm not going to do any specific examples of these. They're very similar to the example that I did earlier in this video. And it's also very similar to what you learned in chapter 4. Just replace your t's with n's and your j omegas with e to the j omegas and use the tables from chapter 5 instead of the tables from chapter 4. I think you'll do fine.